Space is vast, it is filled with wonder, it is also home to objects of immense power. Black holes are among the most fascinating. They are cosmic entities where gravity reigns supreme. Imagine a place where even light cannot escape. This is the reality of a black hole. Black holes are not empty voids. They are regions of space-time with incredible density. Their gravitational pull is so strong that nothing can escape their grasp. Not even light, the fastest thing in the universe. Black holes challenge our understanding of physics. They push the boundaries of our knowledge. Their existence has been confirmed through decades of observation and research. They remain one of the most captivating mysteries of the cosmos. The story of black holes is a journey. It is a journey into the depths of gravity and the nature of space-time itself. It is a story that continues to unfold, revealing new secrets with every passing discovery. Stars are the cosmic furnaces where elements are forged. They live for billions of years fueled by nuclear fusion. But even stars have a lifespan. When massive stars exhaust their fuel, they meet a dramatic end. As a star runs out of fuel, the outward pressure from nuclear fusion weakens. Gravity, always present, takes over. The star's core collapses inward. This collapse happens incredibly fast. It triggers a supernova explosion. This explosion is one of the most energetic events in the universe. It can outshine an entire galaxy. Sometimes the remaining core is massive enough to form a black hole. The core continues to collapse under its own gravity. It shrinks until it becomes infinitely dense. This point of infinite density is called a singularity. This is the heart of a black hole. Imagine approaching a black hole. It's a one-way trip. As you get closer, the pull of gravity increases. Eventually you reach a point where there's no turning back. This is the event horizon. The event horizon is the boundary around a black hole. It marks the point where gravity is too strong for anything to escape. Not even light can escape its grasp. Once you cross the event horizon, you're destined to fall into the singularity. Albert Einstein's theory of general relativity predicted black holes. It describes gravity not as a force, but as a curvature of space-time. Massive objects like black holes warp space-time around them. This warping is what we perceive as gravity. The event horizon isn't a physical barrier. It's a region of space-time, where the curvature is so extreme that all paths lead inwards. It's a point of no return in the universe. The concept of black holes didn't emerge overnight. Long before Einstein, scientists pondered the existence of objects so massive that even light couldn't escape them. These early ideas laid the groundwork for our modern understanding. In the 18th century, Jean-Michel and Pierre-Simon Laplace independently proposed the idea of dark stars. These were hypothetical objects with such strong gravity that they were invisible to telescopes. Michel and Laplace based their ideas on Newton's law of gravity. They reasoned that if a star were sufficiently massive and compact, its escape velocity would exceed the speed of light. While their concepts differed from our modern understanding of black holes, they introduced the intriguing possibility of objects that were invisible to conventional observation. These early ideas paved the way for future generations to explore the mysteries of gravity and the nature of light. Section 5, Schwarzschild's Legacy, Mapping the Geometry of Black Holes. Albert Einstein's theory of general relativity revolutionized our understanding of gravity. It provided the theoretical framework for black holes. But it was Carl Schwarzschild who, in 1916, found the first exact solution to Einstein's equations that described a black hole. Schwarzschild's solution, known as the Schwarzschild metric, describes the gravitational field around a spherically symmetric, non-rotating mass. It provided the first mathematical description of the space-time geometry around a black hole. The Schwarzschild metric predicts the existence of the event horizon and the singularity at the center of a black hole. It lays the foundation for our understanding of how black holes warp space-time. Schwarzschild's work was a pivotal moment in the history of black hole physics. It moved these objects from the realm of theoretical speculation to the realm of mathematical possibility. His solution remains a cornerstone of modern black hole research. Section 6. Hawking radiation. Black holes aren't entirely black. Black holes were thought to be inescapable cosmic sinks. Nothing could escape their grasp, not even light. In 1974, Stephen Hawking proposed a revolutionary idea. Black holes emit faint thermal radiation due to quantum effects. This is known as Hawking radiation. It arises from virtual particle pairs near the event horizon. One particle falls in, the other escapes. The escaping particle carries away energy. This causes the black hole to lose mass over time. Hawking radiation was a groundbreaking discovery. Black holes can evaporate over incredibly long timescales. Section 7. Accretion disks. The luminous signature of black holes. Black holes reveal their presence through interactions with surrounding matter. Matter forms a swirling disk of gas and dust known as an accretion disk. Accretion disks are incredibly hot and luminous. As material spirals inward, it heats up and emits intense radiation. This radiation can be detected by telescopes. Accretion disks often outshine entire galaxies. They signal the presence of these otherwise invisible objects. Studying this radiation helps astronomers learn about black holes. Black holes come in various sizes. Some are stellar mass black holes formed from the collapse of massive stars. Others are supermassive black holes, millions or even billions of times the mass of our Sun. These supermassive black holes reside at the centers of most galaxies, including our own Milky Way. They are thought to play a crucial role in the formation and evolution of galaxies. One of the most well-studied supermassive black holes is Sagittarius A*. It lies at the heart of the Milky Way, about 26,000 light-years from Earth. By observing the motions of stars orbiting around Sagittarius A*, astronomers have been able to determine its mass with remarkable precision. Supermassive black holes are enigmatic objects. Their origin and growth are still active areas of research. They serve as powerful reminders of the immense scales and mysteries that the universe holds. Section 9. The no-hair theorem, simplifying complexity. Black holes, despite their complex nature, can be described by surprisingly few parameters. This simplicity is captured in the no-hair theorem. It states that once a black hole forms, it loses all information about its past, except for its mass, electric charge, and angular momentum. Imagine throwing a complex object, like a book, into a black hole. According to the no-hair theorem, the black hole would retain no information about the book itself. It would only remember the book's mass, charge, and any spin it might have imparted. This theorem implies that all black holes with the same mass, charge, and spin are indistinguishable from one another. They lose all other identifying features. The no-hair theorem has profound implications for our understanding of black holes and the nature of information in the universe. It suggests that information about the objects that fall into a black hole might be lost forever. Section 10. Spinning black holes, angular momentum, and frame dragging. Not all black holes are created equal. Some spin rapidly, while others are stationary. The rotation of a black hole has significant effects on the surrounding spacetime, leading to intriguing phenomena like frame dragging. Frame dragging, also known as the lens-Thirring effect, is a prediction of general relativity. It states that a rotating massive object drags spacetime around it. Imagine a spinning ball submerged in honey. As the ball spins, it drags the honey along with it. Similarly, a spinning black hole twists space-time in its vicinity. This twisting effect can influence the orbits of nearby objects and even affect the propagation of light. Frame dragging is one of the more subtle predictions of general relativity. Its effects are weak and difficult to detect. However, astronomers have observed evidence for frame dragging around rotating black holes, providing further confirmation of Einstein's theory. Section 11. The Information Paradox, a Cosmic Conundrum. The black hole information paradox is a perplexing puzzle. Quantum mechanics says information cannot be destroyed, but black holes lose all information about objects that fall into them. If black holes evaporate, what happens to the information? Does it disappear, violating quantum mechanics? Or is it preserved in the outgoing radiation? This paradox highlights the conflict between general relativity and quantum mechanics. Solving it could deepen our understanding of the universe. One proposed solution is the holographic principle, which suggests information can be encoded on a two-dimensional boundary. This idea has profound implications for our understanding of reality. Section 12. Unmasking the invisible modern black hole research. The study of black holes has entered a new era of discovery. With new technology, astronomers probe these enigmatic objects in unprecedented detail. The Event Horizon Telescope made history in 2019 by capturing the first image of a black hole's shadow. This achievement provided visual evidence for black holes and their event horizons. Gravitational wave astronomy lets us hear black hole mergers. These ripples carry information about merging black holes. Advancements in theoretical work expand our knowledge of black holes. Black holes captivate our imagination and push the boundaries of understanding. Delving deeper into these mysteries reveals the wonders of the universe.